This is section 16.2, the acid bases properties of water. So now we're going to look at an interesting aspect of water, and that is that water can undergo an interesting reaction. One way of writing the equation for what water does is to imagine that it is breaking up into the hydrogen ion, which again we call the proton, right? So that's called the hydrogen ion. And the hydroxide ion just breaks up into those two ions, breaks apart. And we would call that auto-ionization. We would say that water undergoes an auto-ionization process in itself, in water, where it breaks up into two separate ions. Now, from the perspective of Bronsted-Lowry chemistry, acid-base chemistry, we talked about that in section 1, perhaps a better way to write this would be to think that there are two water molecules reacting with each other, and that one of the water molecules is transferring or donating an H plus ion to the other water molecule to form the hydronium ion and the hydroxide ion. Remember, this is called hydronium, and this is the hydroxide ion. So this is a different way of representing the auto-ionization of water. Either it breaks up into two separate ions, H plus and OH minus, or two water molecules collide and form a hydronium and a hydroxide ion. Whichever one you want to think of is fine, but we can say this, that for, we'll call this reaction 1 and this one reaction 2. For reaction 1, if we wanted to write out the expression for K, we would write concentration of H plus times concentration of OH minus. If we wanted to do it for equation 2, it would be concentration of H3O plus times concentration of OH minus. Hydrogen ion concentration times hydroxide ion concentration, or hydronium ion concentration times hydroxide concentration. What you'll find is that in this chapter and the next, this one will be more common, this expression for K. So equation 2 is the one that we'll use more often. Now, it turns out that these are equilibrium constants. We could call them KCs because they're concentrations, but because this is such an important equilibrium constant, we're going to call it KW. We're going to give it its own subscript. And we're going to claim that at 25 degrees C, at 298 Kelvin, that's essentially room temperature, it's been measured out, and to 2 sig figs, it's 1.0 times 10 to the minus 14, again at 25 degrees C. Okay, so this is a measured value. It's a value you should memorize, 1.0 times 10 to the minus 14 at room temperature. It does vary with temperature. If the temperature is higher than 25, it'll increase, but only a little bit. So even if you're doing calculations at 37 degrees C, which is often referred to as metabolic temperature, even then you would use 1.0 times 10 to the minus 14, unless you were doing some kind of very precise calculations. Okay? Now, here's what we're going to claim when we take a look at this. The product of these two concentrations is equal to a constant, which means that these two concentrations are related to each other. And so we could write it in this way. We could say that the concentration of H3O plus is 1.0 times 10 to the minus 14 divided by the hydroxide concentration, right? What that means is if you know the hydroxide concentration, you can calculate the hydronium concentration. Likewise, if it's the opposite, if you know the value of the hydronium concentration, you can use this expression. So if you know the hydronium concentration, you can figure out what the hydroxide concentration is. And I'm going to go through some convention here, terminology, and that is if these two concentrations are equal, they would be 10 to the minus 7. And the reason for that is the only way to get this equal to that and the product equal 10 to the minus 14 is if they're both equal to that. And so if these concentrations are 10 to the minus 7 molar, we call that a neutral solution. A neutral solution is one in which the concentrations of hydroxide and hydronium are equal to each other, which at 25 degrees C would be 10 to the minus 7 molar. If the concentration of hydronium is greater than the hydroxide concentration, then we call this an acidic solution. So there's more hydronium than there is hydroxide. We call that acidic. And if the concentration of hydroxide is greater than hydronium's concentration, we call that basic solution. Or alkaline. That's another term that's used, an alkaline solution. Okay? So if they're equal concentrations, that's neutral. If the hydronium is greater than the hydroxide, practice saying those words to yourself. Hydronium, H3O+, hydroxide, OH-. If hydronium is greater than hydroxide, it's acidic. If hydroxide is greater than hydronium, it is basic.